Our next speaker is Kelly, and he's going to talk about operational interpretation of sandwich Renyi Divergence over the 1/1 as a strong Converse exponent.
Okay, so thank you. This is based on our joint work with my PhD student, Renyi Divergence. I will be focusing on the sandwich divergence, known as the minimal divergence. It's discovered 10 years ago, and turns out very useful. For example, it appears it has appeared in many codes of this conference. So usually for Renyi divergence, the order I is a range from 0 to 1 and from 1 to infinity. Here we have to be more careful because for the sandwich Renyi divergence, it behaves very well when the range is from 1/2 to 1 and from 1 to infinity. Because it means when the ice properties for the range for the order in this range. For example, it satisfies the data processing inequality. It is convex and monotonically decreasing with respect to the stage sigma, and it is monotonically increasing with respect to the order I. Also, the limit cases are very interesting. For alpha goes to 1, there is a sandwich Renyi divergence converges to the sandwich Renyi divergence converges to the ordinary quantum relative relationship. And when alpha goes to infinity, then it converges to the max relative relationship divided here, and we will put back to this quantum later. When alpha is 1/2, then it is the mean relative relation between the related function. Moreover, the two ranges, the two intervals from 1/2 to 1 and from 1 to infinity are related by the order duality. So for instance, the two intervals are 1-to-1 correspondence governed by such a relation. So from 1/2, we are satisfied to just restrict the order alpha to be in the range from 1/2 to 1 and from 1 to infinity. The sandwich Renyi divergence is a fundamental quantity because it is very useful, but most importantly, because it has precise operational implications. For alpha bigger than 1, it has been shortly after the discovery of this quantity that characterizes the strong Converse is problems for example, for hypothesis testing, for communication over CQ channels, for data population, quantitative information, and also for behavioral consistent communication over general quantum channels. And more recently, we also found that it also characterizes the reliability functions for quantum information decoupling, for quantum channel simulation, and for quantum parameters application. I will explain the physics of the strong Converse components and the reliability functions later. In contrast, however, for the order alpha from 1/2 to 1, we didn't know any populational limitations for the established Renyi divergence. And in this book, we will provide the first one for the established Renyi divergence in this case. So our answer is that the established Renyi divergence is what I have to one actually characterizes the strong Converse exponents for certain quantum information for the CC testers. This includes the smoothing of the maximum integration also for and quantum privacy application and quantum information recovery. Before going through the details, let me explain what the strong Converse exponent and what the reliability function. The two together actually are called in general the error exponents. So let's consider the canonical theory of the general resource theory. Suppose that we have many copies of certain kind of imperfect resource, and we want to convert them to perfect ones, or we want to generate them by consuming some perfect resources. Usually, we can identify an optimal rate for the resource transformation. And at one side of this optimal rate, the error probability goes to 0 as quantity, and at the other side, it goes to 1. So the error exponents are the basic explanation rate of such convergences. And when the error probability goes to 0, it is called the reliability function. And when the error probability goes to 1, then we call it the strong Converse exponent. I also need some more entropy quantities. So once we have the established Renyi divergence, then we can define the established Renyi conditional entropy and the established Renyi mutual information via standard weights. So these two entropic quantities are defined for about compact quantum states, for about compact quantum states rho FE. Here for the established Renyi conditional entropy, we have optimization over the stage of the D system. And for the established Renyi mutual information, we choose to optimize both the states on the A system and the B system. Of course, there are some other definitions regarding the optimization, or we can have even no optimization for the local states. But these two quantities are the relevant ones for our purpose. So let me go through the quantum taskers and the strong Converse exponent. We have introduced the maximum iteration. So the smoothing is to try to minimize by changing the stage law a little bit within the additional 4 centered as a stage law. Here we choose the measure to be the purified distance. So it gives us entropy quantity as a function of the smoothing quantity epsilon, and we can consider its inverse function, which is the smoothing quantity as a function of the entropy quantity. the motivation to consider this quantity is because it serves as one of the main tools in one-shot information theory along with the, for example, information signature relative hypothesis relative and so on. But moreover, it has precise operational meaning in the characterizing of the approximate distribution codes. So the smooth equality can be regarded as a quantum version of the error probability. We define the strong Converse. We define the strong Converse as part of the mass relative entropy smoothing as the basic explanation or rate of the convergence of the error towards 1. And we solve this problem and find that the strong Converse is problem is given by the established unit divergence of order from 1/1. So the second quantum task is about the quantum Converse application. Suppose that two parties, Alice and Bob, share a chemical represented by a random variety of x, which may be not maximally least, and part of the information we have linked to adversary system stored in her quantum system. And we wanted to extract a perfect key, and the way to do is by performing task functions to map the random variable of x to z of a smaller size. We measure the performance by employing a certain distance between the final key stage and the ideal key stage, which is maximally unmixed and with no combination with the adversary system. Here we choose the purified distance again. So given the size of the extracted key, we can define the basic performance measured by the purified distance, also optimize over all possible task functions. So this serves as a quantum error probability for a problem, and we define the strong Converse is common similarly as the rate of the convergence of the error towards 1. Our result for this problem is that the strong Converse is common for the low key stage low XE is given by a formula in terms of the established really conditional entropy of order from 1/2 to 1. The last quantum task is about the quantum information decoupling. So quantum information decoupling is about the bipartite stage rho RA. Here the R system is formed by a reference and out of our reach, and we can only access the A system. We wanted to try to remove all the combinations between the R system and the A system. Here we the way to do is to make a unitary transformation of the A system and then discard subsystem A to subsystem of A. More generally, we can consider the category city where we have an additional and additional system whose stage is independent of the stage rho A should help us. As discussed in the last talk on the quantity information economy, the variety quantcast has lots of applications, ranging from quantum theory to quantum thermodynamics and statistical physics, and even black hole physics. Here we we define the strong corpus as colored in a similar way, with the error defined for these codes, which is the size of the discarded subsystem, and optimize the overall possible company strategies. And then we can divide the strong corpus as colored in a similar way. Our answer to the strong corpus for quantity information company given by such a formula it is in terms of the regularized version of the sandwich related history information. Here we don't know whether the sandwich related history information additive or not over tensor coordinates against. So we here add a regularization in such a way. Okay, I have only time to speak some words on the proof. So we to derive our results, we employ two different methods. And one for the smoothing of the maximum entropy. For this problem, we reduce the general problem to the spatial commutative case by exploiting some properties of some new properties of the fidelity and the function and the maximum entropy. And then we solve the problem by using the type method. And for quantum cryptography application and quantum information company, we treat the durability pattern of the validity pattern separately. The durability pattern is somehow more technically involved. We employ Masoni orthogonal approach to solve it. And for the optimality part, we use the technique of natively reordered data by using the very nice inequalities involved in the fidelity and some other sandwich-related quantities. Okay. So I wanted to make some additional comments on the formulation of our problem. Let's consider the problem of quantum application. In the definition of the error function, we have optimized the distance over the adversary system state. And so correspondingly, in the solution, we have the established really conditional entropy also optimized over the stage of the E system. I would say that such a definition is crucial to get the operational definition of the operational interpretation of the established really divergence quantity for our purpose. Well, the case is actually we fix the adversary, the stage of the adversary system, then we may have a solution with the established really conditional entropy replaced by a new version with no optimization over the adversary stage here. But we have a country example to show that this cannot be true. The country example is by checking the classical states. And similar thing occurs for the problem of quantum information company. We cannot expect that by fixing the reference, the stage of the reference system here, to get an answer with the established really mutual information replaced by a new version also with no optimization over the reference system. For this problem, the country example is about the pure states of raw I won't go much into the details. Okay, so let me talk a little bit about the quantum generalization of the really divergence. In principle, there can be many quantum generalization of the really the information divergence due to the non-commutativity of the two states rho and sigma. To identify each of the quantum generalization is significant and non-trivial. But we already have two quantum versions which have precise operational meaning. One is the established really divergence that we have talked about, and the other one is really divergence and one here. It takes some years to get the stage of the atom and the study of this issue. In the year 2006, operational interpretation to the basis version has been found, and people may guess that this quantity is outstanding and could be the unique quantum version of the really divergence. But things changed on the year 2013 when the established version has been discovered and also its operational interpretation has been found in characterizing the strong Converse exponent. More recently, we found that the established really divergence of order bigger than 1 can also characterize the uniformity function rather than the strong Converse exponent that was known previously. And as a result of this work, we found that established really divergence also admits operational interpretation when the order is wrong, 1/2 is 1. So the last picture represents the up-to-date basic understanding of this issue. I have two questions. The first one I would like to ask what is the final picture of the quantitative organization of the Renyi divergence? We may understand the data by studying the area exponents for more quantum information tasks. And most specifically, we wanted to know whether there are more quantum divergences just have precise operational implementation. For example, we have the geometry Renyi divergence and we have the non-Euclidean Renyi divergence, which both of which are very useful, but we don't know whether they have operational meanings. Also, the cases Renyi divergence also have very nice properties when the order I from 1 to 2, and we guess that very likely has operational implementations in this case, and but this is still open question. My second open question about the activity of the salvage Renyi mutual information in our case for the order block 1/1. If this quantity is additive for tensor coordinates space, then we can remove the regularization in our answer to the Converse exponents of the quantum information company. Also, we didn't know, and as you can see, my work asks me whether what's my case, and as a just time, I didn't know, but now I believe it to be true because the additivity does hold for two other cases. One is for the order from 1 to infinity. This is shown by Hao Zhou and Li Gao, and quoted by in Hao Zhou's talk. And another case is the classical case for the whole range of the order shown by Tamamika and Bayashi some years ago. Is a classical case.
Please wrap up because time is over.
Okay, so thank you.
Let's time for one quick question. If
in your work with Hayashi, you show that we have 80% of the max divergence. I noticed that the coefficients are different from the strong number exponent. For the reliability function is alpha minus 1, and for strong number exponent alpha 1 minus alpha over alpha.
Yes.
In the application simplification, for reliability function is no optimization for sigma b, but for strong numbers, there is a optimization.
Yeah. Yes, this is strange. I think for the coefficient, we understand it better because this actually case the range is from 1 to 2, and this actually case usually the coefficient alpha minus 1 lies between 0 and 1, and this is just the value of this case. And for this alpha 1 minus alpha over alpha also lies between 0 and 1 for our case. But for the optimization, I really don't know. It's very strange.
okay, let's thank you, speaker again.